Good morning. I am Dr. B. Ravi Chandra. In the last class, we have discussed about FIR filter and the design of FIR filter using some two different methods. One is direct form method and another one is cascade method. The same thing, the another method to design the FIR, finite impulse response. In this lecture, we will see about one more method, which is nothing but Fourier series method. How this finite impulse response will be designed by using the Fourier series method. We will see the steps design of FIR filter using Fourier series method. Some steps will involve in that, how this design is going to take in place. So after knowing the pattern or after knowing the design pattern and steps, let me have a small look on the problems. I have taken two problems so that we will get a clarity how the design is going to take place. So two topics today in this class. So one is design of FIR filter using Fourier series method. So after knowing these steps, let me have a small look on two problems, how the high pass filter and low pass filter will be designed by using the Fourier series method. Let's start with the design of the FIR filters. First one, let's see here, the frequency response. So I have taken the frequency response h of e power j omega with a periodic of 2 pi. Okay, so I have taken the frequency response h of e power j omega of a system, one system with a frequency response of h of e power j omega with a period of 2 pi. Keep it in mind, with a period of 2 pi, one frequency response I have taken, that is nothing but h of e power j omega. It is a system. Okay, so in that particular system frequency response, I have taken one desired frequency. So I am calling that desired frequency. So I have taken one desired frequency response in that FIR filter system, and I am denoting the desired frequency as hd of e power j omega. So first of all, I have taken total frequency response of a system, FIR system. So it is the total frequency response of a FIR system, which is nothing but h of e power j omega. In this total h of e power j omega, just I am taking a small amount of, that means on desired frequency response of a FIR filter I am taking, and I am denoting it as hd of e power j omega. So what is that equation? hd of e power j omega is equal to summation n is equal to minus infinity to infinity hd of n, which is the impulse response of that system, e power minus j omega n. So this is the first thing we have to keep it in mind. And first, in any problem, the problem will be given with starting of desired frequency, that is nothing but hd of e power j omega. Fine. So first step, what we come to know a small desired frequency in total frequency response of h of e power j omega, which is nothing but hd of e power j omega. Now after getting this hd of e power j omega, now I am taking the Fourier coefficients and impulse response. So if you see here, in desired frequency hd of e power j omega, I am taking the impulse response hd of n. See here, the Fourier coefficient, which is nothing but hd of n, represents the desired impulse response. Okay, what I am taking the desired impulse response in the desired frequency response. Okay, so this is the desired frequency response hd of n. Okay, hd of e power j omega. In this hd of e power j omega, I am considering the desired impulse response. So what is this desired impulse response? It is denoted as hd of n. So what is the equation? It is computed as hd of n is equal to 1 by 2 pi integral minus pi to plus pi hd of e power j omega into e power j omega n into d omega. So what is this? This is nothing but the desired impulse response in that particular desired frequency response. So how it is going to get? How we are going to get this impulse response means by taking the Fourier response of this particular hd of omega, hd of e power j omega. So if I take the inverse Fourier transform, of hd of e power j omega, so what I am going to get? I am going to get the hd of n. How we are going to get the impulse response? If I am taking the inverse Fourier transform of this particular desired frequency response hd of e power j omega, that is converted into hd of n, which is nothing but the desired impulse response. Now this hd of n, this desired impulse response, corresponds to a non-causal filter. That means, so what is the equation of this particular hd of n? It will be in the form of a non-causal filter. That means it is in infinite duration. How? That is h of z is equal to summation n is equal to minus infinity to plus infinity hd of n z power minus n. That is, the formed desired impulse response is in the form of a non-causal filter. That is, it is in a infinite duration. So what we need to do, it is in a infinite duration, but we are dealing about the finite impulse responses, so that infinite should be converted into a finite impulse response. For that, what we are going to do, we are doing the truncating for FIR filter. In the previous equation, it is a non-causality or a infinite duration, but what we need to do, we are dealing about the FIR filter. That's why that particular equation will be truncated. How we need to truncate? So to truncate, that means to get the realizability of FIR filter, to get the realization of the FIR filter, that particular infinite duration should be converted into a finite duration. So for that, what I am doing, I am truncating the hd of n. So how I am truncating? The desired impulse response h of n is equal to hd of n. So here I am truncating mod n less than or equal to n minus 1 by 2. So in that scenario, the value will be hd of n, otherwise the value will be equal to 0. That means here I am converting the infinite duration into a finite duration, which is a countable. That is, in this periodics, that is mod n less than or equal to n minus 1 by 2, in this periodic the value will be hd of n. That is, it is a countable, otherwise it will be a 0. That means here I have done the truncation, so that infinite duration is converted into a finite duration. So this makes the sequence finite and implantable. Okay, so it makes the sequence finite, and we can realize that particular FIR filter. So here, one more we need to keep it in mind. If the impulse response is symmetrical about n is equal to 0, okay, this property you need to keep it in mind. If the impulse response symmetrical about n is equal to 0, the value of h of minus 1 will be equal to h of n. This is an important point. While you are doing the problems also, you need to keep it in mind that if the symmetrical n is equal to 0, then the value of h of minus n will be equal to h of n. So here the transfer function, that is h of n, is converted into h of z, and what is the final equation I am going to get? H of z is equal to h of 0. Why? Because it is symmetrical about n is equal to 0. H of 0 plus, we have truncated from where? From n is equal to 1 to n minus 1 by 2. Okay, less than or equal to n is equal to 1 to n minus 1 by 2 h of n z power minus n plus z power n. So this is the finalized equation, which is nothing but the finite impulse response. Fine, it is good, and we got the transform equation for a symmetrical impulse response, which is nothing but h of z. But here you can see one problem. What happens here? If you see these bracket terms, you can see the positive z power n. So the positive powers is there, where it shows it is not in a causal mode. That means I can call this system as a non-causality. Why? Because due to the presence of these positive powers, this system is said to be a non-causal. So what it is saying, this transfer function is still not physically realizable. Though we have converted into h of z, but we cannot able to realize this. Why? Because due to the presence of positive powers, which we can also said to be a non-causality system. So for this, what we are going to do, we are multiplying this h of z. We are multiplying this h of z with z to the power of minus n minus 1 by 2. That means I am writing it as h inverse of z, which to make the filter realizable, that means from non-causality to causality, what I want to do, I need to multiply this h of z with z power minus of n minus 1 by 2. Then it will be converted into h inverse of z, where this h inverse of z will be a completely conversion of the causal filter. The finalized equation what I am going to get here is h inverse of z is equal to, what I am doing, I am multiplying z to the power of minus of n minus 1 by 2 to the formed transferred equation h of z. So z of minus of n minus 1 into h of z. So by multiplying, it has formed as h inverse of z. So now this is the perfect realizable system where we can convert this FIR filter from h inverse of z into a realization, and we can draw the particular block diagram. So this is the scenario of the total design, how this FIR filter is formed by using the Fourier series method. See here, we can see the complete pipeline of this FIR filter design using the Fourier series method. First, what we have taken? We have taken the desired frequency response of a system HD of e power j omega. From this desired frequency response of HD of e power j omega, I have taken frequency response. I have taken the desired desired impulse response, that is HD of n. So from this HD of n, I have taken the inverse Fourier transform so that it is converted into the h of n, where it is in infinite duration. So in this step, what is the equation? The equation is in infinite duration and the system is in a non-causality system. So for this purpose, what I have done, I have truncated this particular h of n into a countable, that is finite duration, so that after truncating this equation and you applying the symmetrical rule, it is converted into a h of z. So fine, here though it is converted into the transfer function h of z, but it cannot be realizable. Okay, it cannot be realizable. So to achieve this realizability, what I am doing, the formed h of z is multiplied with a factor which is z to the power of minus of n minus 1 by 2, where this h of z is converted into h inverse of z. That means what happens here, this h of z is multiplied with z to the power of minus of n minus 1 by 2. Then I can say that this is the perfect transformable equation where this equation can be realizable to get the FIR filter. So this is the total scenario and total steps involved in the design the FIR filter by using the Fourier series method. Hope you have got these steps involvement here. So this is the finalized thing. We have taken the impulse frequency response of a system. From this impulse frequency response of a system, I have taken the desired frequency response. From this desired frequency response, I converted it into impulse response. From this impulse response, the truncation has been done, and after doing the truncation, it is converted into the transfer function h of z. Though this is a h of z transfer function, it cannot be easily realizable because of the presence of the positive powers. So to convert this non-causality transfer function into a causality thing, that is infinite duration to finite duration, what I am doing, the formed transfer function h of z is multiplied with a power factor, that is z to the power of minus of n minus 1 by 2, so that the perfect transfer function h inverse of z is formed. Now this h inverse of z is purely realizable. So this is all about the steps that involves how this FIR filter design is used by using the Fourier series method. Okay. Now to get good clarity, some more good clarity about this particular design, let me take one example of one problem, so that you will get a good clarity about this design purpose. So before going that, we have a disadvantage. Yes, we have a disadvantages because of this Fourier series method. What it is telling, during the truncation of the infinite series results in oscillation in both the passband and stop bands. We will get some different types of oscillations in passband and stop band scenario. So in passband as well as stop band, we will get some oscillations. So why this oscillation? At the time of truncation, that means we are converting from infinite duration to finite duration. We are dividing that. So we are taking some countable values, where in that scenario some different types of oscillations is formed, that is in both passbands as well as the stop bands. So this formation of this oscillation due to this truncation is said to be a Gibbs phenomenon. So keep it in mind, it is very important terms, that is Gibbs phenomenon. It is nothing but is a process of forming the oscillations in both the passband and stop band while doing the truncation in the design of FIR filter. That process, that phenomenon is said to be a Gibbs phenomenon. We will get in a external questions or else as well as a gate question, it will be obtained. Okay. So this is one of the main disadvantages of this Fourier series method. So for every disadvantages there will be one solution. So for this or also for this Gibbs phenomenon, we can reduce this Gibbs phenomenon. How we can reduce this Gibbs phenomenon means by multiplying the truncated impulse response. That means we got hd of n is equal to h of n. So this is the truncation what we have done. So here what we are going to get, we are getting the Gibbs phenomenon. So to reduce this Gibbs phenomenon, I am multiplying this truncated h of n impulse response with windowing function. There are different types of windowing functions. There will be a Hamming function, Hanning function, Blackman, triangular, some different types of windowing functions are there. So if we multiply any one of the windowing techniques with the desired truncated impulse response h of n, then that particular ripples or that particular oscillations in the passband and stopband will be reduced. So this smooths the transition and minimize the ripples in the frequency response. So there is a disadvantages in this design of FIR filter by using the Fourier series method, that can also be reduced by using one technique which the truncated impulse response is multiplied with the windowing functions. We will discuss these windowing functions in the upcoming lecture, but now just keep it in mind what is the disadvantages and how these disadvantages can be reduced by using the multiplication of the windowing function. Fine. So now we got a clarity about the steps of the design of FIR filter by using the Fourier series method. Let me have a look with one problem. This is nothing but, just take the statement, design an ideal low pass filter with a frequency response. HD of e power j omega is equal to 1. When it will be 1? Within the limits minus pi by 2 less than or equal to omega less than or equal to pi by 2. Otherwise it will be 0. So in that scenario, in that periodic condition, the ideal low pass filter with the frequency response HD of e power j omega will be equal to 0. And he asked, find h of n for n is equal to, capital N is equal to 11, and determine h of z and h inverse of z. This is the statement. So how we are going to design the ideal low pass filter by using the Fourier series method. Now take the step. We will go with step by step. As I told you that in the particular problem, whatever the problem, he will directly gives the desired frequency response, that is HD of e power j omega, and the value is equal to 1. When it will be 1? When in the conditions between minus pi by 2 less than or equal to omega less than or equal to pi by 2. So by giving this desired frequency response, what is the second step? We have to find out the impulse response. I showed you the pipeline of the thing. First they will give HD of e power j omega, they will give. From this we need to find out the value of HD of n. So this is the second step. So what we are doing here, we are computing the ideal impulse response from the given HD of e power j omega. So what for that I have taken, we know the equation for HD of n is equal to, in the first slide we showed that HD of n is equal to 1 by 2 pi integral minus pi by 2 to pi by 2 e power j omega n d omega n. Now after doing this integration, it will be 1 by 2 pi. After doing this integration for e power j omega, it will be e power j omega n by jn within the limits minus pi by 2 to pi by 2. Applying the limits, upper limit minus lower limit, and this jn will be comes outside, and it will be e power j, instead of omega I am writing it as pi by 2 into n minus e power minus upper limit minus lower limit na, so e power minus j pi by 2 into n. So I am taking this 2j inside and I am rearranging the above equation, that is 1 by pi n. 1 by pi n e power j pi by 2 n minus e power minus j pi by 2 n by 2j I have taken into inside the bracket. So it is in the form of, this equation is in the form of one identity which is nothing but e power j theta minus e power minus j theta by 2j is equal to sin theta. So okay, with the help of this condition I am writing this equation as sin theta. What is sin theta here? Theta is nothing but the pi by 2 into n. So this theta is equal to pi by 2 into n. So instead of sin theta, I am writing instead of theta pi by 2 into n. So what is the equation I got here? Final result, ideal impulse response HD of n is equal to 1 by pi n. It will be same. Sin theta, theta is nothing but pi by 2 into n within the limits minus infinity to less than n less than infinity. So we found the value HD of n from the desired frequency response HD of e power j omega. This is the second step. So from HD of e power j omega, we computed the value HD of n, which is nothing but the ideal impulse response. So you can see here the condition lies between minus infinity to plus infinity, but our agenda is we are designing the FIR, that is finite, but it is in infinite. So for that what we need to do, we have to truncate that HD of n to 11 samples. Why? Because he had given the value of n is equal to 11. So to convert that infinite into finite, we need to truncate. So we know that how to truncate this value. That is, after doing this truncation, that HD of n will be converted into h of n. I told you, h of e power j omega is given. From this, we found HD of n, which is in infinite. So to convert into finite, we are doing the truncation where HD of n will be converted into h of n. So what is the truncation formula? We know that the condition from truncation is h of n is equal to, it will be HD of n when for mod n less than or equal to n minus 1 by 2. And we know the value here 11. So 11 minus 1 by 2, that is equal to 10 by 2, which is equal to 5. That is, after truncating, the value h of n is equal to HD of n for mod n less than or equal to 5. Otherwise, it will be equal to 0. So this is the finalized truncated value, that is h of n is equal to, what is the value of HD of n? In the previous step, I got HD of n is equal to sin pi by 2 n by pi n. Okay, so it will be sin pi by 2 n by pi n for mod n less than or equal to 5. So let it be the third equation. What we have done here, we have truncated that particular HD of n so that it is converted into h of n. So after truncation, what we have to find out, with the help of property, we discussed that, I told you to keep it in mind, the symmetrical impulse value for n is equal to 0, for all the values, h of minus n will be equal to h of n. So how many values we have to design here? 5 values, that is h of 0, 1, 2, 3, 4, 5. Total n is equal to 5 values, we have to find the symmetrical impulse values. So for h is equal to 0, by substituting the value of h of n, so h of n is equal to, here what is the equation? We know that h of n is equal to sin pi by 2 into n by pi n. So for substitute n is equal to 0, substituting all the values in n is equal to 0, the first value h of 0 will be equal to 0.5. And with the help of this symmetrical property, we need to find out all the value of h of 0, 1, 2, 3, 4, 5, which h of n will be equal to h of minus 1, h of 2 will be equal to h of minus 2, h of 3 will be equal to h of minus 3, and so on up to h of 5 is equal to h of minus 5. That means if we substitute either 1 or minus 1, either 2 or minus 2, 3 or minus 3, whatever, by applying these two values in this HD of n, in this HD of h of n, then the values what we are going to get is h of 0 is equal to 0.5, 1 for the value of 1 or minus 1, the value will becomes to 0.318, and for all the values, this is the symmetrical impulse values by substituting from 0 to 5. So third step, what we found all the symmetrical values. Now going to the another step. So after doing this using symmetric in the transfer, we know that h of z is equal to, for n is equal to 0, h of 0 plus n is equal to 1 to n minus 1 by 2 na. So n minus 1 by 2, the value will become 5, summation n is equal to 1 to 5, h of n, z power n plus z power minus n. So here, which is nothing but the transfer function we got. But I told you, due to the presence of positive powers z of n, it is not totally realizable. It is very difficult to realize these type of transfer functions, and we can say this particular function is non-causality. Okay, this first particular equation is in non-causality form. So due to the presence of these positive powers, it is very difficult to realizable. It cannot be realizable. So for this, we came to know that. So I have expanded this equation. After expanding this equation, just I will write here. So h of 0, we know that already it is there, plus h of 0, sorry, we start with 1, h of 0, we started with 1, already h of 0 is finished. Now h of 1 into z plus z power minus 1 minus, so I will write directly, plus h of 2 into z power 2 in plus z power minus 2 plus h of 3 into z cube plus z power minus 3, and similarly for plus h of 4 into z power 4 plus z power minus 4 plus h of 5 into z power 5 plus z power minus 5. So after expanding the equation, this is the thing we are going to get. By substituting all the values, we know that what are the values? Zeros. You can see there is 0 for h of 2 and h of 4. The value is 0. So that's why by substituting h of 2 is equal to 0 and h of 4 is equal to 0. So if I substitute it is 0, the remaining is h of 0 which is 0.5, h of 1 which is 0.3183 and h of 3 which is 0.106 minus 0.106 and h of 5 which is 0.06366. So after expanding and after substituting all the symmetrical values, the finalized equation what we got here is this one. So you can see here, by seeing this particular equation, you can see z cube, z power 5, all the positive power factors are there. So it is very difficult to realize this kind of transfer function, and we say that these systems are said to be a non-causality system. So what is the solution to overcome this problem? We have to multiply this particular thing. We have to multiply that particular thing with z to the power of minus of n minus 1 by 2. Okay, so by multiplying this z to the power of minus of n minus 1 by 2 with the formed factor h of z, so what is n minus 1? That is 11 minus 1 by 2, that is 10 by 2 kada? That is 10 by 2, which is z to the power of minus 5 into h of z. That is, the formed equation is multiplied with z to the power of minus 5. After doing this multiplication, you can see the finalized factor which is h inverse of z. So 0.06366 into z power minus 10, z power minus 8, z power minus 6, z power minus 5, minus 4, minus 2, so on. So you can see there is no positive terms, that is positive factors. So with this, what we have done, we have converted the h of z into h inverse of z, so that the non-causality function into causality function. So with the help of this particular equation, it is very easy to realize the FIR filter, so without having any positive power terms. So here, this is the finalized equation what we got, and which is in a causality mode, and we can realize this thing to design the FIR filter. So with this is one of the example which how this high pass filter can be, low pass filter can be realized with the help of, designed with the help of a Fourier series method. So just we will go with the same thing, how this ideal high pass filter will be designed. In the previous we have designed the low pass filter. Now how this ideal high pass filter will be designed by using the Fourier series method. So same, I told you, they will give the desired frequency response hd of e power j omega, that value will be equal to 1, and given n is equal to 11, and they asked to find out the value of impulse response. That is, first hd of e power j omega will be converted into hd of n, small hd of n, and after this hd of n, we have to find out h of n. Of this, after this h of n, this will be truncated and it will be converted into h of z. But it is not, it is in the form of non-causality, so that what we are doing, we are multiplying this with a factor z to the power of minus of n minus 1 by 2, so that it will be converted into h inverse of z. So he has to find out all these things. Let's see what happens here. Same, given the desired frequency response hd of e power j omega is equal to 1. So from this, this is the pipeline. Already we told that hd of e power j omega they have given. From this we are going to find out the impulse response hd of n. From this desired impulse response we are going to get the truncated impulse response. So this truncated impulse response, after doing the truncation, it will be converted into h of z, where it is not in a non-causality mode, it is in a causality, non-causality, so that it will be converted into causality system by multiplying the formed transfer function with z to the power of minus of n minus 1 by 2. So this is the pipeline, how we have to find out the values of all the terms, how we need to converting all this hd of e power j omega to h inverse of z. So in the first step, already they have given hd of e power j omega is equal to when? See here, when it is pi by 4 less than or equal to omega less than or equal to pi. If we see here, if it is minus pi to minus pi by 4, the value is 1. And if it is plus pi to plus pi by 4 to pi, the value is 1. and if it is minus pi by 4 to pi by 4, you can see the value will be equal to 0. So whatever the value which lies between pi to pi by 4 or minus pi to pi by 4, the value will be equal to 1, otherwise the value will be equal to 0, which shows that it is a ideal frequency response of the high pass filters. That's what he is saying. The plot shows HD of e power j omega versus omega. Okay, so on the x-axis we have taken the omega, on the y-axis we have taken the HD of e power j omega, and according to this, the value will be equal to 1 for the two ranges. For the two ranges, one is minus pi comma minus pi by 4, this one, and another one is pi by 4 to pi, this is the one. For these two ranges, the value will be equal to 1 and the value will be equal to 0 for the range which lies between minus pi by 4 to pi by 4. So these are the two ranges which shows the ideal frequency response of the high pass filter. So after knowing these values, let me convert this particular HD of e power j omega to get the HD of n. So we know the value of equation of HD of n already we have seen, that is 1 by 2 pi integral minus pi to pi HD of e power j omega into e power j omega d omega. So by using this condition in that particular integral part and doing the derivations, what we are going to get the final value. See here, after doing the integrations and applying the upper limit and lower limit for that formed integrate equation, we will get one term which is e power minus j pi by 4 n minus e power minus j pi by n by jn. So according to the identity, we will get this one. So it is nothing but sine theta, and this is also nothing but sine theta. Here the theta value is equal to pi n, okay, the theta value is equal to pi n, and here the theta value is equal to pi by 4 into n. So instead of theta, I am writing sine pi n minus sine pi by 4 n, which lies in the conditions minus infinity to plus infinity. So what is the equation we found here? HD of n. From which equation we found here? HD of e power j omega. So from this equation we found the value HD of n, which is nothing but this one, and it lies in the limits minus infinity to plus infinity. So it is in the infinite duration. So what we have to do here, to convert this infinite duration into the finite duration, we need to truncate the formed value. So after doing the truncation value for n is equal to 0, same in the previous thing what we found, we are truncated these things by getting the value, here given the value n is equal to 11, so truncating the value mod n less than or equal to n minus 1 by 2, that will be equal to 5. That is h of n is equal to HD of n, that will be present when mod n is less than or equal to 5, otherwise it will be equal to 0. So after truncating this particular thing, let me find out all the symmetrical values by substituting h of 0. So what we are going to get, h of 0 is equal to 0.75, and after that similarly by computing all the symmetrical values, already we seen that the symmetrical property for n is equal to 0, h of minus n will be equal to h of n. And how many values we have to find out here? For n is equal to 5, total 5 values, 1, 2, 3, 4, 5, up to 5 we found the values 0, 1 minus 1, 2 minus 2, by substituting whether 1 or minus 1, 2 or minus 2, 3 or minus 3, 4 or minus 4 and so on, the values what I got here is this one. Okay, so what are the values I got here? H of 0, H of 1, H of 2, H of 3, H of 4 is equal to, the value becomes 0, and H of 5. So by getting all the symmetrical value and expanding this equation, so this is the equation what we got. So here from HD of n we got H of n, okay, H of n, and from this H of n we got H of z, and you can see all the positive factors, all the positive power terms is there, that is z power 2, z power 3, z power 4 and z power 5. Z power 4 is equal to 0 now, that's why that term has not been considered. So it is not, cannot be able to realize these particular things. So for this what we are going to do, we are multiplied that equation with z to the power of minus of n minus 1 by 2, and we know that n is equal to 11. So by substituting n is equal to 11, with which factor we are multiplying it? We are multiplying it with z to the power of minus 5 to h of z. So by multiplying this total thing, all the positive terms, which positive factors, powers will be converted into a negative ones, and you can see there is no positive power terms here. All z power minus 10, minus 8, minus 7, minus 6, 5, 4, 3, 2, 1, which all it will is in negative terms. That means here this h of z After multiplying it with z to the power of minus of n minus 1 by 2, it is converted into h inverse of z. So after this conversion, it is formed as a causal. It is formed as a causal system. Okay. Now it is very easy to realizable this equation, which is h inverse of z, so that particular ideal high pass filter can be designed by using the Fourier series method, and this is the pipeline what we have seen done up to now. That is hd of e power j omega. It is considered, and we found hd of n. From this hd of n, we found the truncated h of n. After getting this truncated h of n, it is h of z is formed, where this is converted into h inverse of z, which is finally which it can be realizable easy. So this is all about the Fourier series method. That means how this finite impulse response can be designed by using the Fourier series method. Okay. In the next class, the same design of FIR filter is taken place with the help of windowing techniques. I told you, we have seen in the second slide the disadvantages of using this Fourier series method, that is some different types of oscillations is present in the pass band and stop band. So to overcome that oscillations, that is to reduce that Gibbs phenomenon, what we are doing, we are multiplying the desired impulse response with the windowing techniques. That is hd of n is equal to h of n into w. That w is said to be a windowing techniques, and there are different types of windowing techniques which we will discuss one by one in the upcoming lectures. Thank you.